coming to give a talk in England right after a field trip to some moors. I couldn't resist the humor. Okay, so not a Hobbit's tale, but pretty close. Okay, so what I want to talk about. So we've seen so far a number of talks from a very data-driven perspective about traits, some talks about models that included traits. I want to come at this from a slightly different perspective because in my lab we very much live both in the field and with models and really made a niche for ourselves in how we bring the two together. So I want to tell a tale about how we bring models and data together beyond talking about one specific model, but talking about how we could do this for a community of models, kind of an approach rather than a specific model result. And I'm going to call this the model data feedback loop. And so this starts, so our journey starts by characterizing the variability in traits. We then propagate that uncertainty that we have in model parameters that are informed by traits. We analyze those uncertainties to identify which traits and which processes drive our predictive uncertainty. And then we can use that information in a very targeted way in experimental design to target what additional trait data gives us the most additional bang for the buck. So where should we invest our resources? So that's the and back again part. So coming back from models to informing additional field work. Throughout this, I'm going to highlight how we do this in the informatics system my lab has developed in collaboration with a bunch of other folks. It's called Pecan. It's a system for bringing models and data together in many ways. I'll talk about the trait stuff mostly through this talk, because it's a trait meeting after all, and highlight some of the other parts of the system right at the end. Pecan is designed to bring many models together with many data streams, so it is one tool to rule them all. Okay, so our journey begins with Bayes' theorem, because what good journey doesn't begin with Bayes' theorem? Because it's an inherently cyclical approach to inference. We start with priors, we add data, we update those, and we get our updated posterior inference. So in the Pecan system, we treat every parameter in a model fundamentally as a probability distribution. So everything starts with specifying priors for every parameter in a model, which is usually a challenge for most modelers because they haven't stopped to think about their parameters in that perspective. There's often a default value, and you'll notice we often do things like this represent a non-uniform distribution, resisting the urge to say, this thing is between here and there. We often know better than that. So for example, this prior for SLA came from some work we were doing on biofuels, and we said, well, biofuels are, we're specifically looking on switchgrass, a perennial grass. A lot of the work was done on perennial grasses, and we said, well, the global distribution of graminoid SLA is probably a good estimate of what we are likely to see for switchgrass. So parameters can come from a variety of places, expert elicitation, but it's worth stopping to think about what the parameters in a model actually mean and how they can be distributed. So within the Pecan system, our analyses are done on plant functional types because most models work on that basis. But in our system, it's a very flexible format because you can represent a PFT defined based on three fundamental things. First is, what model does it go to? The second is a list of priors associated with that, with the parameters for that model, and then a list of species associated with that. And we allow PFT to be any arbitrary list of species. So we actually do have a PFT called all plants. It's every species registered in our species table. So if you wanted to do one global PFT, we have additional analyses being done through some work of a former postdoc of mine, David LeBauer, looking at high throughput phenotyping in an agricultural setting. They have PFTs defined at the subspecies level. The system doesn't care. So we start from that list of species, and then we query our in-house trait database. This represents not just a variable name in units and value. We can also assign sample sizes and error statistics. We can say where it came from in terms of site and citation. Is it been quality controlled? Do we have, what level of access do we want to give the public to this data? So can the data be restricted or free to redistribute? Everything that's green there is a link to an additional table in the database. So for example, if I look at the citation, I can see where that data came from. And then if I click on that URL, it'll actually take me right to the actual original citation. So why I'm bothering to tell you about this is because it represents two fundamental things that are kind of key to the approach that we're taking here. One is accessibility. So all of this is done through some web-based interfaces to an underlying database. So it's fairly accessible, fairly intuitive. The other is traceability. So when I first started working with these larger process-based models, I would encounter lots of parameters. And you'd wonder where these things came from. And sometimes they were whole numbers, which is both terrifying and reassuring because you know they're made up. So you don't have to look for where they come from because they're clearly made. You find ones that have decimal points, and you say, sometimes you're lucky, there's a citation that says where that comes from, and you might track that down. If you're lucky, the number is in that paper. That's actually a very lucky circumstance because sometimes it sends you to another paper, and then another paper, and then suddenly it's like 1869, and you're like, I found the number. Or you find something that had some arbitrary and confusing transformation between, you're like, oh, you don't know where. So that frustrated me. I was like, where do these numbers actually come from? So we enforce a whole system of fundamentally traceability back to where the model's parameters come from. The other thing that frustrated me was that if I could look up where this parameter came from, it's like, why did it come from this one study rather than another study? So what we then did was we said, well, we want to use the data from across multiple studies, so we built a hierarchical Bayesian meta-analysis to synthesize data across studies. So what we do is we fundamentally say we have data, and this could be raw observations, or in many cases, since we were starting with things we gleaned from the literature, because we started this before TRI was open, or it's still semi, we won't get into that. So we can take raw data, but we can also take summary statistics and sample size for a true meta-analysis. And what we do is we partition this out. So one thing we can do is we can separate within site or study variability from across site variability. We can separate effects of experimental treatments within sites. We can accept this beta GH is a greenhouse effect, accounting for the fact that greenhouse studies or potted plant studies or chamber studies can have systematic biases relative to background values. And this is useful for understanding, for example, the scale of variability in our trait data and how it's distributed. But for most models, what we're interested in is the overall mean. And so here's an example of starting from the gray value is that SLA prior I started with for switchgrass. I've updated that based on the data that was in our database for that species, and we have an updated posterior. So when we first started doing this years ago, we just wanted to get it working. And so all these analyses were done PFT by PFT and trait by trait independently. Though actually, before I go on, I do want to point out that one thing that is nice here is that all of this is completely automated. So you just define the PFTs, you go to run a model, it just happens in the background. Those parameters are re-updated anytime the system detects new data in the trait database. You dump in new data, the model parameters automatically get updated. You don't have to actually go do anything, which is a handy feature. Okay, but like I said, they were initially done on a univariate basis. So what we've done more recently is extend this to now a hierarchical multivariate version of the same model. Hierarchical because now we can run it we add an additional level to the hierarchy where we can estimate multiple PFTs at a time, so account for the covariance structure across plant functional types, as well as the covariance structure within each plant functional type. And the across PFT covariance is intended there to capture higher level emergent relationships among the PFTs, as well as potentially, if you have a large number of PFTs, to borrow strength, to say that there's some overall pattern, and if I have functional groups that are more data deficient, they will be more informed by the overall arching relationship. For today, what I want to focus on is an analysis led by my grad student, Alexei Shiklemanov, who has a poster out there on his spectral stuff. He gave you his lightning talk yesterday. So he's also deeply involved with this. And what Alexei did is he started just to demonstrate how this works with 7 leaf traits taken from TRI, focusing on, I would call kind of structural, stoichiometric, and kind of ecophysiological parameters. He constructed 7 global PFTs. And we've actually run this analysis on both an area and mass-based basis just to see how it differed. And we did this with what's called multiple imputation, which is basically gap filling with uncertainty propagation. So all of our results that I'm going to focus on today look something like this. So for example, here is the correlation coefficient between N mass and J max on a mass basis. For these 7 PFTs, they all have a strong positive correlation, all around about 0.5. That's a nice strong correlation, except the overarching across PFT relationship, which has a negative correlation, which is a really interesting emergent phenomenon. So this idea that this relationship within a PFT can be very different than the relationships within PFTs. If we look at everything, because there were 7 PFTs, so just to orient you, these are all panels like the ones I looked at earlier. I've divided this into a lower triangle, which are the area-based analyses, and an upper triangle, which are the equivalent mass-based analyses. And I just want to highlight a few things. I'm not going to spend the whole rest of the talk on this, so don't worry. So high level, we definitely notice that there are often very different correlations within plant functional types versus across them. So that global correlation is often very different than the one within the PFTs. The trait that really highlights this the most is J max, which, whether it's on a mass base or an area basis, you often have very contrasting and often opposite sign correlations within versus across PFTs. We also know that there's a considerable variability among PFTs. Here we can get this just by looking, in one sense we can get this by looking at the correlation coefficients and see that, the relationships within any given PFT are often quite variable. The other thing that I'm not showing here is that if I actually look at the magnitude of these covariance matrices, most of the variance is at the PFT level. The cross PFT level is much more constrained. So the PFT level means the relationship across them is actually, they're fairly close to each other. There's not that much variability. And we do note some changes between area-based relationships and mass-based relationships. A good example of that is the VC max J max relationship, which is almost completely negative on an area basis, mixed but largely positive on a mass basis. And Alexei will be getting that paper back into review fairly soon, so you guys can all see the gory details. The other thing I want to talk about in terms of how pecan ingests traits is that we deal with things that are kind of true traits and things that we measure on plants directly, and I'll say we deal with things that I would call kind of quasi-traits, things that meet kind of Belinda's definition of thing that we put into a model's parameter as one definition of a trait, but not the thing we measure directly. So an example of that would be, for example, VCmax and Jmax. They are not actually things you measure. These are things you get by fitting response curves. So I'll quickly mention that Pecan has another hierarchical Bayesian model just dedicated for fitting the Farquhar model, can fit light curves, ACI curves, both at the same time. And it also fits this hierarchically, so it can fit this accounting for our leaf-to-leaf variability and covariance at a hierarchical level. We used this a few years ago to look at how the relationship between VCmax and leaf N changed within species, within PFTs, and then across PFTs. So for example, here you can see each of these dots in a line around it is a single species, and the relationship within that species between VCmax and leaf N. The colors are different PFTs, so that you can see the slope of that relationship within a PFT is often very different than the slope within a species. And then the dashed line is the across PFT relationship, which again falls on a third slope different than the within PFT or within species relationship. To me, really highlighting that when we talk about relationships among traits, that it really matters that we identify what scale we're talking about, because there's not one relationship between N and VCmax. It depends on whether you're talking about a seasonal response within a species versus a community assembly response versus an evolutionary response. We also have a module for assimilating leaf spectral data, the stuff Alexei has on his poster. One thing I'll note is, it was on the last slide too, there's URLs of the repositories for each of these. All of these actually have fairly decent vignettes that will show you how you can use the tools. So this is Prospect, if you're not familiar with it, is a semi-mechanistic model for identifying, for relating concentrations of different sort of carotenoids, chlorophyll, water, dry matter, number of layers in a leaf with the spectral properties. And you can invert these to identify parameters, those parameters, and then relate those parameters. You can treat them as traits, or you can relate them to other traits. And then we also have a module for dealing with allometric equations, which again aren't quite traits themselves because they're lines, but allows you to synthesize across kind of again a meta-analytical model. Okay. So the point of all of that, again, was to characterize and synthesize the variability that we have in traits for the purpose of trying to constrain model parameters. So what do we do next? Well, then we want to say, well, how do we make a prediction based on that? So if you treat all of your model parameters as probability distributions, you don't have one prediction anymore. You have a whole distribution of predictions. We do this, again, in an automated way through brute force Monte Carlo methods. We sample from those multivariate parameter distributions. We run ensembles of models, and then we can summarize across them. So at each, in this case, at each year, you could have, at each point in time, we could have a full probability distribution, which we might then summarize in terms of simple summary statistics like a confidence interval, a mean or a median. If you are used to basic statistics, the idea of putting a confidence interval on something should seem obvious. If you have been using process-based models, this is pretty new. We're not very good at actually saying what confidence do we have in our process-based models. I think it's something that the measurement community should be demanding of us. How confident are we? If you see a model that just has one line, is that plus or minus 5% or plus or minus 500%? Well, the reality is, when we first put models into Pecan, it's closer to 500% most of the time. Most of these models are vastly over-parameterized. They'll have scores to hundreds of parameters, often with very little data constraint on those parameters. And when you first start putting these confidence intervals, they can exceed the range of all of the available data. The take-home for me was there is no point looking at model structural uncertainty if all possible data is within the confidence interval. Until you can reduce the parametric uncertainty, you can't say much about structure. And that runs counter to a way that a lot of us have been taught to build models, which is when we see a discrepancy between what the model predicts and what we observe in reality, we usually solve that by adding more things to the model. That reaction is counterproductive. So one thing we also learned from basic statistics is that there is a trade-off in basic model selection between complexity and error. So if you think about a model increasing its number of parameters, and this doesn't matter whether it's a process-based model or a statistical model, as the number of parameters increases, the residual error goes down. We all know that if we have n data points and fit an n-degree polynomial, we can make it go through every single data point perfectly. The residual error is 0, but we have an utterly useless model. And we have an utterly useless model is because the parameter error goes up continually with the number of parameters. And so that implies there is always an intermediate complexity where our predictive uncertainty is minimized. And what I want to push against is the tendency to put more parameters in these models that are justified by the amount of data we have in hand. Again, that tendency to solve problems by adding complexity. We probably need to step back and simplify to actually reduce the total predictive uncertainty. And we need to bring more data to bear. Okay, so how do we bring more data to bear? So, well, first what we want to do is figure out what data do we need to reduce these uncertainties. To do this, I'm going to do what I'm going to do an uncertainty analysis. I'm going to take the uncertainty we have in the model parameters that's coming out of this meta-analysis. I'm going to run a sensitivity analysis. This is, again, something that's automated in Pecan. And I'm going to translate the parameter uncertainty through the sensitivity analysis using Monte Carlo methods to figure out what is my uncertainty in my model's output attributable to one specific parameter in the model. In this case, it's this model slope parameter, what has variously been called either G1 or squiggle. I used to call it M, but I evidently have to update my new terminology. I think I'm going to stick with G1, sorry. But we can do this not just for one parameter, we can do this for all the parameters in a model. And then we can rank them, because what we're going to look at here, okay, so this is our parameter uncertainty, our sensitivity, and our output uncertainty. So big bars are things that contribute a lot to the model output uncertainty. Little bars are things that contribute almost nothing to leaf uncertainty. Again, I'm going to have to pick on Colin, because it turns out leaf width is actually not important. Despite his enthusiasm for it earlier. At least not in this model.
I think you're wrong about the stomatal slope there as well, actually, Mike.
Well, stomatal slope is a really interesting story. Because what you see here in the gray line and the black line is the distinction between the gray being our analysis with the priors and the black being our analysis after we've assimilated the trait data. And so actually what happened with that specific case was we identified stomatal slope as being an important parameter based on the priors. At the time that we did this, I was still at the University of Illinois, and the guy at the office next to me, Andy Leakey, is absolutely obsessive compulsive about measuring stomatal slope. So he sent out his graduate students, and remember, this is one species. This was done on switchgrass, and he did a very intense measurement campaign directed at getting high-quality measurements of stomatal slope. So what you see, essentially, is that Andy was able to reduce the parametric uncertainty on that parameter value considerably. So that's why it drops. Not that it's not important, but that we made a very targeted measurement campaign. And she didn't set me up for, I didn't set her up for that. But that is a great example of how targeted trait data collection can really hone in on individual parameters. We've repeated these sorts of analyses across, this is one model, the ED2 model, but across a whole gradient of vegetation types from southern pine forests up to the tundra, and identified kind of common patterns within this one model of what was driving the uncertainty across the board. And so we found for the ED model, growth respiration was the dominant term across most vegetation sites. We see kind of a second and third was a real importance of this coupling between carbon and water, one being in terms of root water uptake, the other being the stomatal slope. And then we found an interesting, and I think now rectified, issue of data deficiency on light use at high latitudes. This is a couple years out of date. The thing that is coming soon, but wasn't ready for today, is to repeat this now across a much wider range of models and provide some feedback to the community about across the suite of models we're using, what factors, and across biomes, what factors are dominant to, are controlling the uncertainties for our community of models. Cool. So what can you do with this information? Well, obviously you would want to target the things that affect the model's uncertainty first, because you're going to get the most bang for your buck. But you can actually get a little bit more rigorous about this as well. So this is a kind of a thought experiment. So we know that parameter uncertainty is a basic statistical, falls in the basic statistical paradigm of if you keep measuring data, it goes down asymptotically. And so this is what we're seeing here. If we keep sampling a parameter, it's the standard error of that parameter reduces asymptotically to 0. In the context of what we're doing here, we can again translate that from the parameter uncertainty, the uncertainty in the model's prediction. So that's a change on the y-axis there. And we can then allow us to look at different parameters. So I might be able to compare two arbitrary parameters, 1 and 2, and think about, well, which one actually gives me the greater reduction in uncertainty? For something simple like this, where I'm not ascribing any sort of cost to these, we can do a basic marginal cost economic analysis and say, what gives me the most bang for the buck? And it would say, well, if I were to start sampling, I'd want to start sampling variable 2 because I get the most reduction in uncertainty. But at some point, I switch to variable 1 because it then gives me a greater marginal reduction. So you could actually say, for a given cost or a given sample size, say, what is the optimal balance across multiple different parameters that's going to give you the largest reduction in uncertainty per unit effort. And you can also extend this to a more realistic economic analysis where you might be able to ascribe differential costs to differential sampling parameters. So we know that an SLA measurement is going to be a lot cheaper than, say, an isotopic analysis. Okay. And so what we can do then is think about this journey from data to models and back again as an iterative process. So this figure represents our first foray into doing this at high latitudes. A former master student of mine, Carl Davidson, who started by characterizing, synthesizing trait data from the literature, performed analysis, figured out what was most important. Assimilated flux tower data, assimilated growth data from certain experiments, and then designed his summer field campaign based on what was the most important parameters to constrain, went out to Tuluk for a few weeks, and in the end you can kind of see each of these symbols represent essentially a lap through the model data feedback loop, and in the end our overall uncertainty is considerably reduced. Okay, so what's next? So I said I've mostly talked about our trait work, but this is actually the oldest part of PCAN. I want to highlight that, again, this is a multi-model system. The models in white are models that are in the system already or are in process of being integrated. Gray are models that I've got verbal or written consent from the collaborators to put models in. So it's a quite rapidly growing list. And also to say that what we've talked about here, these sort of sensitivity uncertainty analyses, is just part of a larger system that deals with the informatics of bringing data in to systems, does full Bayesian calibration, does full data assimilation in a state assimilation mode, and does extensive system for benchmarking. And more generally is thinking about this question: what observations do models need to replicate? Whether that's bringing in trait data, bringing in observational data, what is it that we want to bring models and data? Where do we want to bring models and data together better? That's all I had. Thanks.